we now proceed to the next important topic with regards to semiconductor fundamentals, and this has got to do with something called as the density of states. Okay. And the idea behind this, if you remember, I see our main goal in this subject is to calculate the current or the current density, let us say. And in essence, this current density is dependent upon the traffic of electrons and holes, right. It depends upon the rate of change of charge. Okay. To first order, this is what we would like to calculate when we apply, when we subject the semiconductor device to different bias conditions. Okay. Now, this traffic of electrons, okay, electron and hole traffic, it depends not only on the speed, but also on the number. Okay. Now, the speed was very nicely characterized by something called as the mobility of the carriers. Okay. But we have still not discussed anything to do with the count on the number of carriers. Okay. In particular, we would like to calculate the number of electrons or holes per unit volume of the semiconductor, and this is something called as the carrier concentration. Okay. So, when we say carrier concentration, we imply the number of free electrons and holes per unit volume. So, we are not interested. So, for example, if this is the conduction band edge and that is the valence band edge, okay, we are only interested in the electrons above the in the conduction band. Okay. And we are interested in the holes in the valence band. We are not interested in the holes in the conduction band. There are plenty of holes in the conduction band, plenty of vacant states, but that is not going to contribute to the current. And similarly, there are plenty of electrons that are bound to the atoms sitting inside the valence band, and they are not going to contribute to the current. So, we are not interested in the electrons. We are interested in the holes in the valence band and the electrons in the conduction band. Okay. So, we want to get a gauge on the number of electrons and holes per unit volume. Okay. And how do we do this? So, this is what our next goal is. How do we know how to calculate speed to some extent, okay, because we know this parameter called mobility, and we know that the drift velocity is the mobility times the electric field. Okay. So, we know how to calculate the velocity, but we do not know the number. Okay. We left that, we simply used the symbols n and p and we left those undefined. Now, the way you go about calculating number is to firstly identify the number of seats or the number of solutions to Schrodinger's equation that electrons and holes can occupy. Okay. So, if you imagine a classroom, okay, which has got let us say there is a classroom, and let us say there are lots of chairs in the classroom, okay, and the students can come and can sit in the classroom, but you make a rule that a student has to sit on a chair. He or she cannot stand in the classroom. So, if the student has to sit on a chair, and if the students can be imagined to be electrons, and you ask the question, how many students, can you take a guess as to how many students are present in a classroom? Okay. So, you need two parts to answer that question. The first is how many chairs are present in the classroom, okay, how many chairs, and the second is what is the probability that the chair is occupied. Okay. So, if you know what these two numbers are, then you have a good estimate as to the number of students in the classroom. And the density of states is going to give you an answer as to the number of chairs, or in fact more accurately it is the number of states per unit energy per unit volume in a 3D material. So, if you are looking at 3D semiconductors, okay, so 3D semiconductors implies your crystalline lattice is quite large. It is much larger than the size of the atom in all three dimensions. Okay. So, let us say for example, if you are interested in a number, let us say it is greater than, much greater than 20 nanometers. Okay. I mean the atom is much smaller than 20 nanometers, but nevertheless as a practical estimate you can consider all these materials to be 3 dimensional. So, you have a lattice that is significantly large in all 3 dimensions. If you have a Cartesian coordinate system and you label this as x, that is y, and this as z, then you have a lattice that is significantly large in x and y and z directions. So, the density of states is going to give you an answer to the number of chairs, so that you know the number of students. Okay. So, it is an important question to answer if you want to calculate the concentration. So, we want to know how many states, and what are states? States are basically the solutions to Schrodinger's equation. Okay. How many solutions are there to Schrodinger's equation per unit energy, okay, per unit volume of the material. And if you have this, what you will end up with is, if you know the energy, if you take 1 unit volume of the semiconductor and you plot the energy versus number of states, the distribution of states in this energy. Okay. So, let us say you plot the distribution of these states. So, let us say you have the density of states, okay, which we will denote by n of E, n as a function of energy, or you denote it as G as a function of energy, or you denote it as D as a function of energy. Sometimes depending on what the mood is, we will just use a different variable, but you will get the context of it. So, it is the density of states, and you have all these states present that are distributed in energy, okay, and we want to know as to what this distribution is. Okay. Is it that is it going to be uniform, or is it that it is going to vary vary as the square root of E, or what is it? What is the distribution of the states as a function of energy in a per unit volume of a 3D material. Okay. So, we will do this exercise first for a 3D material. Okay. We will see how to go about making this calculation, and then we will do the same calculation for a 2D material and for a 1D material, and finally answer questions for a 0D material. Now, what do you mean by a 2D material? It's like it's quite large in 2 dimensions, but quite thin in the 3rd dimension. So, you can imagine a 2D semiconductor, which say you might have heard of, for example, say molybdenum disulfide or graphene, etc. And a 1D material is probably something that's is just thin and long. Okay. It is like a little wire. So, any nano wire could be approaching a 1D material, and a 0D material is something which is conceptually a point. Okay. It's got no dimension on x, y and z. So, you will be a quantum dot would probably be approaching a 0D material. So, we will look at the density of states for all these examples, but for the time being we are interested in the density of states for a 3-dimensional material. And we want to perform this calculation of how many states per unit energy per unit volume, so that you have this distribution, and this tells me the number of chairs or the number of places the electrons can occupy. And after getting this, if I somehow can calculate the probability that an electron occupies a state at a particular energy, I can use these 2 answers to get the count of the number of electrons, which I will then use to calculate the current. So, that is the whole idea. Okay. So, what we will be doing in this exercise is to find out how the density of states, how does n vary with E. Okay. Okay. How does it vary with E? Is it proportional to E, or what is it? How does it vary with E? Okay. So, in order to answer this, we are going to just ask ourselves 5 questions, okay, and we will do the same thing for all the cases. Now, this is for a 3D material. Now, the first question is, how many solutions of Schrodinger's equation, that is how many states are there per unit volume in K space. Okay. So, what is K space? K space, K is the wave vector, okay, in some, and K space is essentially your reciprocal lattice space. Okay. So, we are not going to be looking at the actual material in its spatial coordinates. Instead, we are looking at the reciprocal lattice space. Okay, that is the frequency, the spatial frequency space, if you like. Okay. And we ask ourselves the question as to how many solutions of Schrodinger's equations are there per unit volume of K space. And why is this easy to calculate? Because we have already solved for the wave function in these in K space. So, if you remember your particle in a box, okay, we always will keep going back to that little example. So, we solved the wave function for a particle in a one dimensional box, and we found that the wave function was this, right. So, we got this by normalizing everything, and we got this little term which is nothing but your k of x, okay, and we got this to be a quantized value, and we had to have an integer n, and I have used the subscript x to represent the x direction. Okay. So, you have kx is equal to nx pi by Lx. So, k could only take integer values of pi by Lx, and why should that happen? Because it had to meet the boundary condition of the wave function not existing outside the box. Okay, so that was a boundary condition, but nevertheless k will be quantized no matter what you see or how you define your potential. So, k is a quantized parameter. So, n has got n can only be integers, okay, and therefore, if I were to draw the kx vector, or if I look at the kx space, then I see it can only take discrete points, right. It can have values of pi by Lx, 2 pi by Lx, 3 pi by Lx, and so on and so forth. Okay, and you could also have say minus pi, minus 2 pi, and so on. So, only those values were allowed. And if you solve Schrodinger's equation for a 2D box, okay, we use the technique of separating the two wave functions, the separation of variables, which was we split psi as psi x and psi y, and we found that it was simply a product of these two wave functions. So, here you have kx and ky, and both of them are quantized, and I have defined the quantum numbers as nx and ny, and the lengths of the box are Lx and Ly. And similarly, for a 3-dimensional box, you will have the wave function be a product of psi x, psi y, and psi z, and therefore you will have 3k, kx, ky, and kz, defining your k space. So, here I have just drawn it out here. So, you have the solutions to Schrodinger's equation being discrete points. So, this would be pi by Lx, 2 pi by Lx, and so on. This would be pi by Lz, 2 pi by Lz, and so on. This would be pi by Ly, 2 pi by Ly, and so on. So, you have this 3-dimensional grid of points. So, I have not completed this grid, but you can imagine this 3-dimensional grid of points, and each point is a solution to Schrodinger's equation. So, it is the electrons can only take these values, okay, the electrons can only exist in these states. So, if you were to imagine this 3-dimensional grid, okay, and now each of these are solutions. So, what is the answer to this question? How many solutions of Schrodinger's equation are there per unit volume of K space? So, let us imagine this 3D grid that sort of sits like this. So you have these little cubes, cuboids if you would like. Okay, let me just draw it better. So you will have these little cuboids, and the vertices of these cuboids are essentially the solutions to Schrodinger's equation. So you will have 4 of them sitting right in front, and you could imagine 4 at the back. Okay, you will have 4 at the back. So you have this little region, and if you imagine a point right in the middle of this, okay, it is being shared by the 4 cubes in the front, or and the 4 cuboids at the back. Okay. So one solution, each solution is shared by 8 unit cells of K space, and each unit cell in K space has got 8 solutions. Okay, so there are 8 solutions, each shared by 8 of them. So there are effectively 8 into 1 by 8, which is equal to 1 solution of Schrodinger's equation per unit volume in K space, per unit cell in K space. Okay, we have not yet calculated the volume. So this is this many solutions. So we have one solution per unit cell. Now we need to get the answer as to how many solutions per unit volume. So we need to find out what is the volume of each unit cell, and the volume is simply this product, right? It's pi by Lx into pi by Ly into pi by Lz. So that's the volume. So let me just write it a little better. My apologies. So the volume of a unit cell in K space is pi by Lx into pi by Ly into pi by Lz, which is pi cube by Lx Ly Lz. So there is one solution per unit cell, and that unit cell has got this volume. Okay. Therefore, how many solutions of Schrodinger's equation are there per unit volume? The answer is simply, as far as our calculations go so far, the answer is simply one solution divided by a volume of Lx Ly Lz, I am saying pi cube by Lx Ly Lz, which is Lx Ly Lz by pi cube. Okay. But this answer is you are more or less correct here, but we are still not accounted for several things. Okay, we need to do a small correction. We need to have a correction factor, and the correction factor has got to do with it's got 2 reasons for it. Okay, the first is our integers, the quantum numbers nx, ny and nz, okay, could have plus or minus values. Okay, so you could have plus or minus 1, plus or minus 2, and both these are the equivalent to the same energy. Okay, so we are double counting for the number of solutions. Okay, so in order to get the correct number of solutions, I probably need to take this answer and divide it by 1 by 2 into 2 into 2. I need to half it for each of the dimensions. But then there is also another point. The electrons can have plus or the up or down spin. Okay, it can have 2 spins. So 2 electrons can occupy a state. Okay, so we need to account for that by multiplying a factor of 2. Therefore, the corrected answer is essentially this. Okay, it has to have a term 4 there. So the correct answer to the number of solutions of Schrodinger's equation per unit volume of K space for a 3D material is Lx Ly Lz by 4 pi cube. Okay, so this is the answer to the first question. So now let us proceed. Okay, now we want to know how many energy states or how many solutions exist between K and K plus dk. Okay, so now imagine you have taken your K space. Okay, you have your kz, kx and ky, and you have filled it, you filled the grid up. Okay, you just zoom out of this. So, we were looking at the grid in a very microscopic sense, okay, and we calculated the number of solutions per unit volume, but now I am going to zoom out and I am going to see this massive grid of points, right. It is just going to be a massive grid of points. And if you ask yourselves, okay, what is the locus of points having the same k? Now, this k is essentially, it is essentially the combination of kx, ky and kz. Okay. So, if you ask yourself as to what is the locus of points that have the same value of k in a 3D space. Okay. So, you have got this massive grid of points, and what is the locus of keeping the k constant? The answer is quite obvious. It has to be a spherical shell, or it has to be a sphere. Okay. So, if you were to keep k the same and look at all the points that have got the same value of k, the answer is it is going to be a sphere in 3D space. And what is the region between k and k plus dk? So, this is k. You could have another sphere which has got a radius of k plus dk. Okay. And we are interested in the number of energy states that exist between k and k plus dk. Okay. So, we are interested in the number of energy states or number of solutions to Schrödinger's equation that exist in this region here. We are still in reciprocal lattice space, we are still in k space, and we are looking at the number of solutions that exist in this region. Okay. So, how do we calculate this? Well, I just need to know how many unit volumes are there in this space. I know the number of solutions per unit volume, which is equal to my Lx, Ly, Lz by 4 pi cube. Okay. And I just need to know what is the volume. Okay. So, if this is the number of solutions in one volume, let us say 1 unit volume, how many unit volumes are there in this region I am interested in? Okay, so, what is the volume of the space? The volume of that space is the surface of the sphere into dk. So, which is 4 pi k square dk. So, that is the volume of this space which I am interested in. And how many solutions are there in this volume? The answer is simply Lx, Ly, Lz by 4 pi cube into 4 pi k square dk, okay, which is very neatly written out here. So, there are this many energy states in the region between k and k plus dk. So, which is where k, so we are looking at the reciprocal lattice space once more, where k, where you have kx, ky and kz, okay, and you have all the points that have got the same k to be sphere, because this is a massive grid of points, and all the points that have got a radius of k plus dk is another sphere that is very concentric to this, and this region has got a volume of this much, and there are this many solutions per unit volume, and therefore, there are so many solutions of Schrödinger's equation in this region of interest, just to repeat everything. Okay, so, what is the next question? The next question is, how many states exist between E and E plus D? Okay, so far we have been making all our arguments in k space. Now, we want to convert this information in k space to energy. Okay, because we are trying to estimate the density of states, which is the number of states per unit volume per unit energy. Okay. So, I know the number of solutions to Schrödinger's equations, or the number of states existing between k and k plus dk. I know that. Now can I translate this to the number of states between E and E plus D? Okay, so that's the question. Okay, so if I know this, can I calculate that? So how is K connected to E? K is nothing but your wave vector. So h bar K is my momentum, okay, and E is p square by 2m. Therefore, E is h bar square K square by 2m, and therefore K square is 2m E by h bar square, and K is the square root of this whole thing, which is 2m E the square root by h bar. And what is dk by dE? dk by dE is obtained by differentiating this, right. So you have 2m to the power half by h bar and the differential of e to the power half, which is 1 by 2 e power half, okay. And therefore you have dk is equal to this term into dE, okay. So we have these 4 relations with us. Now what we are going to do is, we know that the number of solutions in this region between K and K plus dk is this. Now we are going to substitute for K square and dk with these expressions in terms of E and dE. So what is K square? K square is 2m E by h bar square, okay. So instead of, so let us keep these terms separate, and instead of K square I am going to substitute 2m E by h bar square, and instead of dk I am going to substitute this particular expression here, okay. And after a bit of simplification, you cancel off say common terms, you will end up with the number of states between E and E plus dE is given by this quantity here, okay. So we now know the number of solutions to Schrodinger's equation sitting between 2 energy levels E and E plus dE, okay. So now let us see how to get to the density of states. Now we ask our 4th question, which is how many states exist between E and E plus dE per unit volume. Now this is the real volume of the material. So we are no longer in reciprocal space. So what is the volume? Okay, now the box had lengths Lx, Ly and Lz. Therefore the volume of the box is Lx, Ly, Lz, okay. And therefore this numerator here is the number of solutions to Schrodinger's equation, or the number of states between E and E plus dE, and this is the volume of the box. And therefore the number of states between E and E plus dE per unit volume is simply that divided by the volume of the box, and that gets rid of the Lx, Ly, Lz terms, and you have these many states sitting per unit volume and between E and E plus dE. Now in order to get the density of states, I need to know the number of states per unit volume per unit energy, okay. So I also need to divide it by the, I also need to get a per unit energy term, okay. And how do I do that? You simply divide it by dE, okay. So you are looking at all the states between here and between E and E plus dE per unit volume, and you divide it by dE, which is the energy gap, the energy region you are looking at, the you know the length of the energy region you are looking at, and you end up with the number of states per unit volume per unit energy to be given as this, which is nothing but the definition of the density of states. So this is the density of states for a 3D material, okay. So most importantly, we must, what you must be looking at is how does the density of states vary with energy. So this density of states for a 3D material scales as the square root of energy, okay. It is proportional to the square root of energy, okay. Now since we will be using 3D silicon as the model material in our course here, it is useful to draw this out, okay. So forgive this very rough sketch which I have drawn here. So for a perfectly crystalline material, you have your valence band edge and your conduction band edge, okay. and in between this is something which we defined as the energy gap. Okay. Now for a perfectly crystalline material, the energy gap will have absolutely no states. It's only when defects start to appear that the energy gap will start getting filled up with states. Okay, but as far as most of the course is concerned, there are no states in the energy gap. It's only when we talk about disordered material late, towards the end of the course will we start worrying about states in the gap, or even when we talk about doping, for example. Okay. But for now there are no states in the gap. So your density of states, which is proportional to E, basically implies this, that there are states above the conduction band edge, okay, which is the bottom of the conduction band, and the valence band edge, which is the top of the valence band. There are states in these regions, and the way the states vary with energy is as E minus EC to the power half. Okay, so you have states varying like this in the conduction band, and you have states varying in proportion to EV minus E to the power half. Okay, you have states varying like this in the valence band. Okay, so that's what it implies. Okay, so this is how the states in. So if you look at the number of solutions to Schrodinger's equation, right at this point there are 0 states, and just immediately after that you have a little bit, and then after that you have a little bit more. And how does it all, how does this envelope scale? It scales as E minus EC to the power half into this particular term here. Okay. And all this M which you have seen throughout is all the effective mass. It should have all been M star. It is all the effective mass which we discussed earlier. And similarly the states below the valence band edge. So these are the, this is the distribution. If you ask what is N of E, what is the density of state distribution in 3D material, perfectly crystalline 3D material, okay, the answer is, it is this when E is greater than equal to EC, that is from infinite to EC. It is this when E is less than, okay, I'm sorry, E is less than equal to EV, okay, but greater than minus infinite, and it is 0 when E is between EC and EV, okay, which is the energy gap. So that is the distribution of the states in a 3D material. Now what about a 2D material? We ask ourselves the same questions, but the only thing is we need to ask ourselves how many states per unit energy per unit area in the material, okay, because we are now looking at a 2D material. We just go through the same process again, okay, and let us see what it gives us. So first question is how many solutions of Schrodinger's equation are there per unit area in K space. So now your wave function is just you are just looking at a 2D box, okay, you are just looking at a 2-dimensional box. So therefore there are only Kx and Ky to worry about in the K space, okay. So you have this grid of 2D points, 2D grid, and if you were to draw, if you let's draw these, connect these lattice. If you look at the unit cells, you have one unit cell here, one unit cell here, one here and one here. Now per unit cell how many solutions do you have? You have 4 solutions which mark the vertices of this rectangle, okay. But each solution is shared by 4 unit cells. This solution for example is shared by this cell, by this and by this. So each solution is shared by 4 unit cells. So you have 1 solution per unit cell, okay. So that is the number of solutions per unit cell in K space. And what is the area of 1 unit cell? Area of 1 unit cell is simply your pi by Lx. So these points are all pi by Lx, 2 pi by Lx and so on, and that is pi by Ly, 2 pi by Ly and so on. So it is pi by Lx into pi by Ly. So that is the area of 1 cell. and therefore, the number of solutions per unit area is going to be simply 1 divided by pi square by Lx Ly, which is Lx Ly by pi square. But once again, just like the last time, we need to make a correction. Okay. Now we are double counting for the plus and minus. So you have Lx Ly by pi square. The plus and minus we are double counting. There are 2 dimensions, so we divide by 1, we half it for each dimension, and there are 2 spins, and therefore you have a corrected or a correction factor of 2 pi square, which defines the number of solutions of Schrodinger's equation per unit area in K space. And now we ask ourselves this next question, how many energy states between K and K plus DK? So what is the locus of points? So now let us take our K space, which is a 2-dimensional space, and fill it up. Okay. So you have this massive grid of points. Okay. You can imagine a graph paper that you might have used at school. You have this massive grid of points, discrete points, and these are all the solutions of Schrodinger's equation. And we want to know how many states between K and K plus DK. Okay, so what is the locus of points on a 2D map, in 2D space? What is the locus of points which keeps K constant? Okay. So K will now be square root of Kx square plus Ky square. So what is this locus of points? The answer is it's a circle. You want to keep the radius constant. So if I keep the radius as K and I draw and I connect all the points that have a constant radius K, it's a circle. And what about K plus DK? It's another circle which has got a slightly larger radius, and it's this. So these are 2 concentric circles. And we want to know how many states are there between K and K plus DK. So we are interested in the number of states in this little ring here. Okay, if you remember the 3D case, we had spheres, okay, because it was 3-dimensional, and we had the spherical shell that was the region of interest. But now, since it's 2D space, you have this little ring. Okay. So what is the area of this ring? The area of this ring is the perimeter of a circle into dk. So that's the area of the ring. Now I know that there are Lx Ly by 2 pi square solutions in 1 per unit area, 1 unit area. So how many solutions exist in 2 pi k dk, in an area of 2 pi k dk? Okay, so the answer is simply 2 pi k dk into Lx Ly by 2 pi square. So this is the number of states existing in this ring, in this region here between K and K plus dk for a 2D material. Okay. So what is the next step? Next step is to convert this all to energy. Okay. So the next question is, how many states exist between E and E plus dE, right? So we know that between K and K plus dk we have these many states, that is 2 pi k dk Lx Ly by 2 pi square states. Now how do I convert all this to the number of states between E and E plus dE? We go through the same process again. So we know E is p square by 2m, which is h bar square k square by 2m, and therefore all these relations follow. And now we substitute for k and dk. Okay, so these are the number of solutions in terms of E. So we use this expression and we use this expression. So that's my k and that's my dk. Okay, so it's 2 pi k dk into Lx Ly by 2 pi square, the number of solutions. So it is this many. When you simplify all this, you get this little neat little answer here, and this is the number of solutions or the number of states present between E and E plus dE. Okay. And now the next question is obviously how many states between E and E plus dE per unit area. Okay. And now the box, okay, now we are looking at a 2D box, and the area of the box is, it has got dimensions of Lx and Ly, and therefore the area is simply the product, which is Lx Ly. There are these many solutions to Schrodinger's equation in the region between E and E plus D, and the number of solutions of Schrodinger's equation between E and E plus D per unit area is simply that divided by Lx Ly, and that gives you this. It is m by pi h bar square d. Okay, so there are these many states present between E and E plus D per unit area, and how many states between how many states in the 2D material per unit area per unit energy, which is the density of states for a 2D material. Okay, the answer is m by pi h bar square dE divided by dE, which is m by pi h bar square. Okay. So, there are these many states per unit energy per unit area in a 2D material. Okay. We have followed the same process as in the case of a 3D, the only thing is we have adjusted terms for a 2D case. But what is fascinating here is that the density of states does not depend on the energy. You do not see an energy term. In the 3D case, we saw that the density of states was proportional to e to the power half, but here there is no, it is proportional to e to the power 0. Okay. It does not depend on energy at all. Okay. So, that is interesting. So, you will find that for a 2D material the density of states is constant with energy.